Hello students, in tomorrow's class we're going to talk about the conservation of momentum. Once more, as you watch this video, make sure you take down notes and pause the video whenever you get lost anywhere to take down notes before you continue with the video. So, what should you learn in this video? You should be able to describe the interaction between two objects in terms of the change in momentum of each object. Second, you should be able to compare the total momentum of two objects before and after they interact. And finally, and most importantly, you should be able to state the law of conservation of momentum. Before we start talking about the law of conservation of momentum, recall the impulse-momentum theorem. What does the impulse-momentum theorem say? It says that the impulse is equal to change in momentum, or in other words, impulse is equal to Ft, right? So the net force on an object will be equal to the rate of change of momentum of the object. Net force is equal to the rate of change of momentum of the object. So if we write it in equation form, we have F equals delta P over delta T, where delta P is the change in momentum of an object. F equals delta P over delta T, where delta P is the change in momentum of the object. Right? That is the impulse momentum theory, which we learned already last week. Now, let's consider the case of collisions. That is when objects collide. A snooker ball, two snooker balls that let's consider two snooker balls that collide head-on with each other. As you see in this photo here, let's consider these two snooker balls that collide head-on with each other. They collide head-on with each other. Before the collision, let the first ball be moving with velocity UA. And also before the collision, let the second ball B be moving with velocity UB. After the collision, let the first ball now change its velocity to VA, and the second ball changes its velocity to VB. So remember, U is initial velocity. So UA will be the initial velocity of A, and UB will be the initial velocity of B. V is the final velocity, so VA is the final velocity of A, and VB is the final velocity of B. Now, we are going to consider the case only at the instant in which they collide, at the time in which they collide. At the instant in which they collide, they are touching each other, we know that the ball A will exert a force on the ball B. Let the force that ball A exerts on ball B be called, let's call it FB, the force on B. Also, ball B will exert a force on ball A. Let's call that force FA. According to Newton's third law, these two forces will be equal in magnitude, but opposite in direction, as we know. Equal in magnitude and opposite in direction. What does that mean? It means that FA should be minus FB. FA should be negative FB because they are opposite in direction, so there's a negative sign here. Now, if we go back to our impulse momentum theorem, FA, the force on A, should be the change in momentum of A divided by the time it takes to change that momentum, and the force on B should be the change in momentum of B divided by the time that it takes to change that momentum. Because the two balls collide and leave the time it takes for their momentum to change is equally the same. So the time will cancel out and we will have the change in momentum of A should be the same as the change in momentum of B, with a negative sign to indicate that the direction is different or opposite. With a negative sign to indicate that the direction is opposite. Now, the change in momentum of A is the final momentum of A minus the initial momentum of A, and the change in momentum of B is the final momentum of B minus the initial momentum of B. Change in physics always means final value minus initial value. So it means that the mass of A times the velocity of A after minus the mass of A times the velocity of A before should be negative the mass of B times the velocity of B after minus the mass of B times the velocity of B before. Yeah, this is the meaning of change. Final minus initial value. Final minus initial value. This equation, we can rearrange it. We can rearrange it to have mass of A times initial velocity of A plus mass of B times initial velocity of B equals mass of A times final velocity of A plus mass of B times final velocity of B. Now, look at it carefully. The mass of A times the initial velocity of A plus the mass of B times the initial velocity of B is the total momentum of A and the B before the collision, right? Yes. And the mass of A times the final velocity of A plus the mass of B times the final velocity of B is equal to the total momentum after the interaction, correct? Yes. So this equation tells us that total initial momentum equals total final momentum. So that is just the law of conservation of momentum. So the law of conservation of momentum, you can state it in words. It says, when objects interact, the total momentum of all the objects remains constant. Doesn't that sound like the law of conservation of energy? Yes, it sounds exactly the same. The conservation of energy says that total energy remains constant. Conservation of momentum says total momentum remains constant. The only difference between the law of conservation of momentum and the law of conservation of energy is that momentum is a vector quantity. So when you consider momentum before and final, think about direction. You must have direction. Choose one direction positive, the other direction must be negative. Now, we have derived this law of conservation of momentum using collisions. This means objects that have collided with each other. This law is equally true for explosions. When objects explode, like two objects are moving together and then they separate from each other. For example, you fire a gun. For example, you fire a bullet from a gun. That is an explosion. So the law is equally valid. Okay, so you should be able to use that law to solve problems. And this is an example problem. I hope you pause the video here and look at this problem carefully. And try to solve it before tomorrow's class, but we will also look at it again tomorrow. Okay, thank you.